Thank you for the introduction. As I said, I'm Miguel Bote from the University of Valladolid in Spain. And today I will be presenting an exploratory work about the prediction of the decrease of engagement indicators in MOOC. So this is the outline of the presentation. After a short introduction, I will present the formulation of our problem and also the approach that we have proposed to tackle it. We will see also the results of experimental. Yes. Sorry. Maybe like this. Is it okay like this? Okay. We will see also the results of an experimental study that we have carried out in order to see the feasibility of the approach that we have proposed. And finally, some conclusions and future work. So let's get started. First of all, I would like you to know that we focus on academic engagement, which refers to the behaviors that can be observed in the students that participate in a learning process. Behaviors such as attentiveness or the completion of assignments. So in the literature, we can also find works on academic engagement in MOOCs. There are some very nice ones that have already defined different engagement indicators that quantify somehow the behaviors observed in the MOOC learners. Some examples of these indicators are just the number of lectures, videos watched, the number of submitted assignments. There are other works that have also identified different engagement patterns using these kind of indicators. For example, you probably know the completers pattern, those students that do everything in a MOOC, or the viewers pattern, those students that watch videos but barely participate in other activities. Some other works have found that the engagement indicators of many learners decay over time. This implies that the educational impact of the MOOC is reduced in these students. Part of these students, but not all of them, are the students that drop out. But there are many other students whose engagement decays, and as a consequence, they do not profit from the MOOC as much as they could. So this is why our goal is to provide some actionable information to fight this decay of engagement. So more specifically, we want to identify those students whose engagement indicators are expected to decrease in a short time, so that we can trigger some kind of intervention that might be, for example, suggesting a video that could be of interest for the student, or maybe providing some hints to solve an assignment. So what we propose in this short paper is an approach to predict this decrease of a student's engagement in a MOOC, with the particularity that we use only data from previous activity in the very same course for which we're going to do the predictions, and only data that is available at the time of making the predictions. In the literature, you can also find some interesting related works about the disengagement detection in intelligent tutoring systems and learning management systems. There is, of course, a big context difference with MOOCs, as you know. And also, the approach is different, because in these works, they try to classify the students according to different states. In our case, we do not pay attention to the states, but just on the issue of the decrease of the engagement. Maybe the student is in the very same state, but the engagement is increasing or decreasing. That's what we pay attention to. Of course, there are also quite a few good works about dropout prediction in MOOCs, or the completion of courses in MOOCs. But here I would like to stress the fact that these works focus, let's say, on a subset of students whose engagement decays, not all of them. Moreover, most research works in the literature use data that would not have been available at the time of prediction. This is the typical approach. At the end of the course, I gather all the data, I make a cross-validation with the data, I train my models, and make the cross-validation. So that the models that are generated that way could not have been used in that course. So the results that are reported, actually, according to other researchers, can be considered an optimistic estimation of the results that can actually be achieved with data that are only available a priori, or approach. Of course, these models could be used, maybe, to make predictions in a rerun of the MOOC. However, other researchers have shown that the results may get worse, quite worse. So let's see the problem formulation. We had to make some assumptions to formulate our problem. The first assumption is that the course is structured in chapters, which is quite usual. And that it has, there is a chapter start that is defined by the day the learning materials are released, and that there is also chapter end that is defined by the day the deadline for submissions is, even if the materials of that chapter are still available after the deadline, which is also quite useful. We also assume that the students are expected to perform different types of tasks, such as video watching, answering quizzes, submitting assignments, and so on. So, under these assumptions, it's possible to define indicators that quantify the engagement of students in that task since the beginning of the course and until the end of a given chapter of interest. So in this way, we can formulate the problem as a classification problem. We want to know at the end of chapter I if the value of a given indicator of a given student will decrease at the end of the next chapter. So the answer will be true or false, binary classification problem. So this is the approach that we propose. It's somewhat complex. I tried to make a drawing in order to help understanding it. I hope I can make it. So as you can see, I have drawn the chapters spanning over time. In fact, chapters that overlap, which is also very usual, marking the beginning and the end of the chapter. And then you see a red line that marks the moment in which I want to make the prediction. So our approach is basically uses the data, the log activity data of the very same course that is available at that moment. So what we do is that we generate some training features of the activity of students until the end of the previous chapter. And we also use labels labels to train our model that indicate whether the engagement of the student decreased at the end of current chapter with respect to the previous chapter. I mean, what we do is teaching a model to be able to predict using data of previous chapter, and then we use it to test or to make real predictions using the features, the test features that describe the activity of the students until the end of chapter I. This approach imposes some constraints that must be taken into account. One of them is that the same set of features must be used to describe the activity in all chapters. And also, we have to be careful so that the features varies always in the same range so that we can compare them. So now the experimental study, we took the data that MIT provided us about the well-known course on circuits and electronics that was delivered in EDX in spring 2013, which spanned along 15 calendar weeks. This was a course that was structured in 14 chapters. All of them had videos and some so-called finger exercises, some quizzes inside the videos. And the first 12 had assignments with a deadline associated to it. In this course, there were nearly 27,000 students enrolled at the end of the course. However, about 6,700 watched at least a video or did at least one of the finger exercises or an assignment before the end of the corresponding chapter. And of all of these, those students, a few more than 1,000, got the certificate showing that they had successfully completed the course. So in this case, what we did was defining three different engagement indicators, one for lecture video activities, another for finger exercises, and another one for assignments. We then generated up to 16 features for each of the first 11 chapters with the corresponding labels stating whether the engagement decreased or not. I want to underline the fact that we excluded all samples that were either obvious to predict or very easy to do that. I mean, as a consequence of the overlapping of chapters, sometimes at the end of a given chapter, we know that a given student, the engagement of a given student will not decrease because he has already done more than he had done in the previous chapter. So we don't use his data to make predictions. We don't need to. Similarly, there is the situation of dropout students. It is quite easy to make prediction for dropout students since their engagement decreases once they drop out with respect to the beginning of the course. So once we see a student has not shown any activity in 3 weeks in a row, we stop including their data in the dataset, so that we have a real prediction problem. What we did next was performing a feature selection using the correlation-based feature selection method. And here you have a graph showing the number of data sets in which each feature was selected. You can see that all features were selected in for at least 2 of the data sets. And we can also see that there are a few more relevant features that eventually could help us understand how this disengagement process takes place. I won't get into details, but some samples are the percentage of lecture videos watched, exercises answered, and assignments submitted. So after the feature selection, what we did was generating different prediction models for each chapter, at the end of each chapter, and for each engagement indicator. What we did was comparing some basic algorithms, more specifically logistic regression, stochastic gradient descent, random forest, and support vector machines. The results are reported in using area under the curve as a performance metric. Because of the same reasons that a speaker this morning in the session at risk explained. We have data sets that are quite imbalanced, so performance metrics add as accuracy or maybe kappa do not work or suffer more from this imbalance than the area under the curve. So that's the reason why we use it. Well, some observations also. We obtain pretty good results with the stochastic gradient descent. In fact, they are comparable to the best results reported for the dropout problem, but in their case, using data that is available a posteriori, while in our case, it's with data that is only available a priori. Some other observations are that you can see that in the first chapters, there is an increase of the performance. We believe that this is due to the disengagement of the so-called strong starters, those students that start working in the first weeks like they were going to do everything, but suddenly they disappear. So it's difficult to predict these strong starters. And we also see some decrease of the performance in the last weeks. And in this case, we think that this was at least partially due to the fact that in this course, the final grade was computed using the highest 10 chapter grades out of 12. So that students that had already had good grades in the first 10 chapters just decided not to go on. So let me finish with some conclusions and future work. In our work, we have proposed an approach to predict the decrease of engagement indicators that hopefully will allow making interventions to prevent it in order to increase the educational impact of MOOCs, in order to, including fostering the completion of MOOCs and reducing the dropout. We have obtained good prediction results, but we are, of course, aware that we have still important limitations that we plan to address. First of all, we only defined 3 different engagement indicators. We plan to define new indicators, and let's see what happens with them, such as, for example, the participation in forums, which is also very important in MOOCs. Of course, this data, these are results with a single MOOC. We should, and we have already started trying in different MOOCs to see whether these good results can be seen also in other courses. There is also an issue with the assumption that MOOC has assignments with deadlines. There are some MOOCs that do not have these assignments with deadlines. So we plan to try to adapt the method to a different definition of chapter end. And another issue is that due to the approach that we have proposed, we cannot make predictions at the end of the first chapter. We have to wait until the end of the second chapter to have enough data to predict our model. We are aware that it's important to have predictions at the first chapter, right? Especially because of the strong starters that I mentioned before. We should try to do something with them, try to avoid the dropout. So we'll tackle this also, proposing a specific approach to predict at the end of that chapter. So that's all. Thank you for your attention, and if you have any question, I will be glad to answer.
So thank you for the work. So how did you train your predictive model? What kind of training data set that you use?
What kind?
Training data set.
Training data set. We just took the data of the activities of students in that course and then derived the features and the training features. This is what I tried to show here, but maybe I didn't do the right way. So once we move on to make here the prediction, what we do is computing the features using the activity of students in previous chapters. We use this activity, we train, we have here the training features, we have here the training levels, trainer system.
Yeah, so my question is, who provided the label? Like, how did you?
We compute the labels because I can compute the engagement here. I can compute the engagement here. If the difference is positive, then the engagement increased. This means that we have a false label. If the engagement decreased, we can generate a true value label.
So this is lead to my follow-up question. So why didn't you just compute everything over time? Why didn't you make a prediction or a classification problem? Why didn't profile the student usage over time and see if the activity or the
You mean
engagement over time decreased or increased?
you mean making just a regression problem in which I try to see try to predict what's the engagement here, and then
Not even a regression or even a classification. Just track the usage. You can just track the usage over weeks and see if it's going up, down. My question is, why do we need to have it as a prediction, a classification problem? It doesn't seem to be a classification problem. See, if you can track the usage over time and look at if the usage increased or decreased.
yeah, but you don't know what's happening in the future. You know what happened until here, but you don't know what will happen here. So it's a prediction problem.
Do you consider there is a linear situation that if the person is decreasing, will decrease?
Yeah, then you will be assuming that it's going to decrease later. But maybe there are cases in which here you have a decrease, here you have a decrease, and then it increases. Yeah.
I guess just to follow up on that, maybe I missed, how did you get your estimates of model performance, like the test performance? How did you obtain those? Were they on a holdout set, or did you cross-validate?
No, what we did is what we would do in the real course. It's measuring the performance for each chapter using just this. We don't need to do the cross validation. I mean, because these are different data sets. There is one different data set for the training, which is the one you can compute at this moment. And then you have a different data set for the test. Completely different and independent.
But in order to train your model, it needs to see the labels.
Yeah,
Right?
yeah, but we don't. The trick is that we don't use the labels of future. We use the labels of the previous chapter.
Oh, the chapter.
Yeah, that's it.
Okay.
That's it.
What do you do if the cases like the chapters are not exactly the same?
Exactly in which way? For example, the length. No, that's one of the constraints that we have to use the same features. So it's a constraint we have to assume with this approach. I don't know. Yeah, sorry.
So you mentioned that one of the sort of assumptions that you're making is that the platform that you're working with requires timed assignments.
Uh-huh.
That's some of the criteria that you're using them. Do you have some idea of how you might modify this to be useful in a platform that's more open-ended? Because sometimes if you don't have dates, then it means the dropout is not necessarily a dropout. It means that you're taking things off and then
Yep. It's a very good issue. We don't have yet ideas. We're still testing this approach with alternative courses to first see if it's really valid with these assumptions. But of course, we will have to face this issue. We are aware that these assumptions do not hold in every course. Yes.
So I guess I have two questions. First, I'm assuming all of the feature categories were used to predict each outcome, right? So you used video engagement, or video exercise and assignment to predict the assignment.
Uh-huh.
I was interested to see if you found any feature types that were better at predicting even outside of their category. And then second, I was interested, I noticed that the performance scores are pretty much the same across the three categories, and I think that's interesting. I would think that some would be easier to predict perhaps than others. And I was wondering if you could discuss what you noticed there, if you had any other results that could shed some light on that, or what your intuition was.
Concerning let me go to the concerning the first question. Sorry.
So I was interested if certain categories of features were good at predicting other categories.
Well, we didn't observe that. Instead, what we observed was that the set of features that were better to predict changed along the course, so that the features that were required to make prediction at the beginning of the course were not the same features that were required at the end of the course. So that was our observation, not the.
Answers that, right? Like video, maybe, and actually all three were important early on.
Yeah.
And then later
Yeah.
it kind of changed week by week. That's interesting.
And the second question was, sorry.
Did you have any intuition behind why the prediction task was kind of equally challenging in each category instead of exercises maybe being easier?
Yeah, well, I would say that at least the results are very similar in the case of especially videos and the quizzes, because they are highly tied in the platform. So these are questions that you answer while you're watching the video. So if you have interest in the video, normally you will answer. So this is my explanation without having looked the details of what this happens. But here you can see that the results are different. Here, this is more difficult to make the predictions, and that's because, well, the segments, you have different patterns of students that just do the videos and do not do the assignments, even if they watch all the videos and they do all the finger exercises. And sometimes you have the opposite case, students that do all the assignments, but that do not watch videos. We don't know if these are students cheating the system. I mean, students that in some way gather the answers with one account and use the other to answer. But we have not dealt with that. Yes?
So, first of all, I think this is really cool, and I think this approach, I mean, it's really important to know what you know at given time. So, I was scrolling your paper to make sure I got it. So the labels that we're predicting are whether each individual feature has a negative slope between time I minus 1,
Not
etc.
each individual feature. It's the engagement for. It's the indicator for each engagement. I mean, there's for each student. At the end of a chapter, there is a label stating whether his engagement will decrease for video, another about whether the engagement will decrease for the exercise, and another for the assignment.
Okay. I have kind of an open-ended philosophical question, if you'll humor me. If you could measure anything you wanted about these students, of course you can't, what would the label you'd like to be predicting be?
What would be the label I would like to predict?
Because I'm assuming that you'd really like to know something about what students are actually doing that we haven't measured.
Probably I would like to predict what would happen with the engagement at the end of the course. But in that case, you cannot follow this approach, because you would have to use the a posteriori approach, seeing what happens in previous runs of the same course. So that's what I probably would like to, as a quick answer, to see.
Do you think that if we could, at the end of it all, train a model against just whether they passed or failed, and then use that model in a future class, do you think that might be useful?
Train the model
With a past class.
with the past class.
Because that's what we want to know, is whether they pass or fail, right?
Not always, because you know that, and that's behind the philosophy of this proposal. There are students with different goals when they make a MOOC. There are students that want to pass. Yeah, that's one of the goals. But there are other students that just want to learn some things, or maybe watch some chapters, or maybe have a general view of something. So this is why we didn't want to focus on performance and on passing or failing the course. Okay, so thank you for all the questions.